Cool. Okay, yeah, we're going to do the second, or our second Zoom session in 110 acoustics, and we'll continue on from where we left off last week. And I see Taylor has joined on. You haven't missed a darn thing. I started recording maybe 5 seconds ago, so you haven't missed anything. So here we go. We'll continue on from where we left off last week in acoustics 110, talking about frequency, wavelength, and all that jazz. So what I'll do is I'll share screen here, and we'll see where it was that we were. Okay, here, let's take a look at that guy here. Share screen, here we be. And last week, we covered this page, and we went down, and we also talked about, we did a bunch of PowerPoint slides too. We talked mainly about how sound waves occur in the air. And we used a tuning fork like this as our example. And we talked about compressions and rarefactions of air molecules. And we called one compression and one rarefaction a wavelength. So if I use my cursor here, one rarefaction, one compression is known as a single cycle of a sound wave. And we showed it in this picture here too, just a different way of showing it, but showing you that sound starts from a source and goes out like spheres. And it's compressions and rarefactions, compressions, rarefactions of molecules. And we said we draw sound waves up and down because it's easier. But really, sound waves don't go up and down. Water waves go up and down, but not sound waves, okay? So the up that we draw on a sound wave, always remember, and put a star by this because this is quiz material, okay? The up represents the condensation, the down represents the rarefaction, okay? So one single cycle is one compression and one rarefaction. And we draw that as one sound wave having 360 degrees. So the sound wave in phase, 360 degrees, 0, 90, 180, 270, 360. And now you're back where you started again, okay? And we showed that sound waves coming out of a speaker this one here is rarefacted first, I guess, so it's sound wave we draw down, and then you've got compression, so now you have the up, and then you have a rarefaction, the down, and then a compression, the up. And this sound wave coming out of the bottom here, we said that has a higher frequency, didn't we? Okay, it has a higher HZ, capital H, small z, that's called the word hertz. That means how many cycles per second did occur. So let's call this 1 second, this time, okay? So on a sound wave, the axes are time on the horizontal and amplitude on the vertical. Time on the horizontal, amplitude on the vertical. So how many cycles do you see in the bottom sound? Well, let's draw. 1, 2, 3, I guess 3.5. So 3.5 cycles per second. So you would say 3.5 hertz. H-E-R-T-Z, hertz. Let's look at the top sound. How many cycles do you see here? Well, we're starting here, going up, then you're going down, and now you're where you started again. You've gone 360 degrees. Okay? How many cycles do you see in 1 second here? Well, 1.5. I guess 1.5 hertz. Go ahead.
I'm looking at this and not.
Yeah, that's all I see too.
Let's see.
I'm looking at the yeah.
You're looking at the PowerPoint?
No, you had the
We're
notes
not
up.
getting the PowerPoint. We're getting your.
Oh, that's odd. Let's see if we can show the PowerPoint then. Okay. Are you seeing it now?
Yes. Not
Beauty.
enough.
I don't know what happened. Don't ask me, but thanks for bringing that to my attention.
Okay, thanks.
Good stuff. Hey, I'll show that again then. Let's talk English here. Okay.
Yeah.
Thank you. You'll see this bottom sound. You'll see one compression, one rarefaction, one compression, one rarefaction, and so on. So let's count how many, let's pretend this took 1 second here. Okay, so how many cycles did you see? Well, let's start here. 1, 2, 3, I guess, whoops, and a half. Here, I guess 3.5 hertz. Capital H, E-R-T-Z. Capital H, little z. Look at the top sound. It began as a rarefaction, now a compression, now a rarefaction, now a compression. So let's count how many cycles you see here. Starting at this one, 1. Now you're back where you started. So now that's 360 degrees. As soon as you get back to where you started, you're at 360. That's 1 cycle. And how many cycles do you see in this second? Call this 1 second here. Well, 1.5. I guess 1.5 hertz. Top one, 1.5 hertz. The bottom one, 3.5 hertz. It really hurts. Okay? So now you take a look at this picture here, and it's showing you 1 cycle of a sound wave as well. And you can see now when you get back to where you started, you're at 360 degrees. Good. That's 1 cycle of a sound. The more cycles per second, the higher the frequency. Here's another picture showing you the cycles, 1 cycle of sound in terms of degrees. Always remember that on a sound wave, the axes are time on the horizontal, amplitude on the vertical. Here's a sound wave in the opposite phase. It's still 1 cycle, but this sound wave begins as a rarefacted and then a compression. Doesn't mean it's not a nice sound wave, it's just a different phase. Here's another sound wave of a different phase yet, but you can see as soon as you're back to where you started, you've got 1 cycle. So if you started here and now you're right back to where you started, you've gone 360 degrees. So this sound wave and this one all have 360 degrees. They're all showing you 1 single cycle of sound. Here's a picture that's a very good picture because it shows you the 3 dimensions of sound. The 3 dimensions. And I'll blow it up so you can see it even more better. Okay? I don't like that bar at the top. Go away. Bar, go there. Okay, away. So look at the top sound. Is it the same in amplitude? What do you think?
Yes.
As it says, I could read it too as well. It's exactly the same in amplitude. What's different about it is the frequency. One of these has way more bumps than the other one. If you call this 1 second from left to right, how they differ is in frequency. Look at the middle ones. They're the same in frequency. They're the same in amplitude. How do they differ?
Time.
Time. Look at the bottom one. They're the same frequency. They're the same phase or time. How do they differ? They differ in amplitude. So sound takes place in 3 dimensions: frequency, intensity, and time. Those are the 3 main dimensions of sound. This picture shows you the same thing. So you've got these 2 differ in terms of amplitude on the top. The middle, they differ in terms of frequency. They're the same height, same amplitude. And the bottom ones are the same frequency and same amplitude. They just differ in phase or in time. Once again. So this picture is the same, shows the same concept as this one does. So now let's get to where we ended up last week, and let's talk about period and wavelength. Those are the things we want to cover today. So we're moving past where we did last week. I'll take a sip of my coffee here. I'll gargle with it, and then we'll carry on. All right. Yeah, we're really formal here. Okay, so let's go to your notes and let's look at the PowerPoints at the same time. We're near the top of page 2 in your notes, probably about a quarter of a way down the page. And let's talk about right here. I'm going to pull here. Let's go down, down. Can you see can you see the notes now or not? Let me know. Okay.
Yeah.
Okay, good, good. Okay, so here we are, amplitude, frequency, and phase, and we've covered those 3 dimensions, okay? And next, in a couple of weeks, we're going to be talking about complex sounds that I've got grayed out. Up to now, we're always talking pure tones, simple sounds, just one frequency, okay? Might be 3.5 hertz, might be 10 hertz, might be 20 hertz, whatever. Complex sounds are sounds like speech, traffic, noise, music. Those have many frequencies together at the same time. But we're not going there yet. We're going to just talk about period and wavelength of simple sinusoids, of individual frequencies. Okay? Now here we go. Right down to the top third or middle third of the page. This is what we're going to cover big time right now. So we're looking at frequency and period. Read at the top, it says, frequency is the number of times something happens per unit of time. Well, I'll stop sharing here. Think about walking. How many footsteps did you take per minute or per second? What was your speed of running? How many times did something happen per some unit of time? Is your unit of time a minute, an hour? In sound, we talk a second. Your unit of time is seconds. So how many cycles occurred per second? Okay? And that's hertz. What hertz was it? 10 hertz? That means 10 cycles per second. 100 hertz? 100 cycles per second. 100 compressions and 100 rarefactions per second. Good. Got it. Now, back to share screen. And the notes. For sound, frequency refers to the number of cycles per second. Hertz. 1 hertz is 1 cycle per second. A sound with a frequency of 100 cycles per second is 100 hertz. Period. Okay. Put a star by this. The time, and now point to your wrist in terms of your watch. Okay? The time, like on a clock, the time it takes to complete 1 cycle. Wavelength is different. Wavelength is the physical length of the sound wave. Okay? So are you looking right here? Okay, period is the time it takes to complete 1 cycle. Wavelength is the physical length of the cycle. Good. Very important to understand that distinction. We're looking at period first. If a sound is 1 hertz, then its period is 1 second. Okay, you had 1 cycle per second. I guess the time it took to complete that cycle was 1 second. Now let's look where this grayed out here. If a sound is 100 hertz, you had 100 cycles per second. That means the period of that sound was 1/100th of a second. Okay, so let's look here. Here's a period. Look at the top one. How long in time did it take to complete 1 cycle? Pretend this is 1 cycle, 1 second, from left to right. So how many cycles occurred? 1, 2, 3, 4. Okay, so what was the period of that? And you'd have to say 1/4 of a second, because you had 4 of them occurring in 1 second. So what was how long did it take to complete 1 cycle? 1/4 of a second. Okay, so the higher the frequency, the shorter the period. They are inversely related. Again, look at the top sound. If this is 1 second from left to right, and you have 4 cycles occurring in 1 second, well, how long did it take for 1 cycle to occur? 1/4 of a second. Okay, so the higher the frequency, the more hertz, the shorter the period. Let's look at the bottom one. How many cycles occurred here? 1, 2.5. Okay, so you had 2.5 cycles in that second. I guess you'd have to figure that one out. So let's go. Here's how you figure it out. Period, frequency, and period are inversely related. As frequency is increased, period is decreased, and vice versa. Frequency, now put a star by this. You've got 3 formulas in this class. This is one of them. Okay, this is your first set of formulas, and I'm going to ding you back and forth on these. You will be quizzed on this, and you will have to make sure that you can do this. It's not complicated. This is probably 6th grade arithmetic. So let's check it out. Frequency is 1 over the period. Period is 1 over the frequency. Okay, so let's do an example. I'll get my calculator here. Cool. Let's say you had a sound and it was 1,000 hertz. You had 1,000 cycles per second. What did we say was the formula? How do you figure out the period? Period is 1 over frequency. Frequency is 1 over period. So what's the period of a 1,000 hertz sound? Here we go. Calculator. 1 divided by 1,000 equals, let's see if I can handle this. There you go. I can see it under my light. There you go. Oops, sort of, kind of. There you go. 0.001 second. Okay? So 1/1000th of a second. A 1,000 hertz tone, a tone that has 1,000 cycles per second. What's the period of that tone? 1/1000th of a second. 0.001 seconds. Oh, you can't see it. You can. You sort of, the glare on here. There you go. Humdinger. 0.001 second. Let's do another one. 500 hertz. Let's say you had a sound that had 500 cycles per second. What's the period of that? 1 divided by 500 equals. See if I can handle that. What do you see? 0.002 seconds. 0.002. Okay? So the higher the frequency, the shorter the period. Let's say you had a sound. Now let's work it backwards. Let's say you had a sound that the period was 0.001 second. Okay? Let's say you had a sound and the period was 0.001 second. What's the frequency? Well, period is 1 over frequency. Frequency is 1 over the period. So 1 divided by 0.001, 1 divided by 0.001 equals 1,000 hertz. P is 1 over F. F is 1 over P. P is 1 over F. F is 1 over P. They are inversely related. Okay? Remember that. You will be asked, and it's not rocket science, but period is the time it takes to complete 1 cycle of a frequency. All right. I think we've beaten that one to death. Now let's talk more about human hearing. Let's talk about us. Okay? Humans hear sounds as low as 20 hertz all the way up to 20,000 hertz. What's the range of human hearing compared to a cat, compared to a dog, compared to an elephant, compared to a bat? What's the range of frequency of human hearing? From 20 cycles per second, or 20 hertz, which is really low, okay, all the way up to 20,000 cycles. 20 to 20. 20 hertz to 20,000 hertz. Now, there's something important I want to tell you all here. In your field, when you become HISs, hearing instrument specialists, okay, humans lose high frequency hearing as we age. And I said last week it's called presbycusis. And I said last week sounds just like Presbyterian. And Presbyterian means Church of the Elders. Presbyopia, I have that. That's why I wear reading glasses. I can't see close up. I'm past the age of 40, so I've lost my close-up hearing. Presbyopia. Here, vision in the elderly. Presbyopia. You are going to be dealing with presbycusis, hearing in the elderly. And elderly people lose treble. They lose high-frequency hearing. They can't hear the birds. They can't hear high pitches. They don't hear the cymbals in the band. They can't hear the of speech. So they can't hear the consonants of speech. When they hear, they're hearing them, and instead of saying, hi, how's it going? They're going to hear, hi, how are you going? Okay, they can't hear the high pitches. When you can't hear the high pitches, they're going to say young people mumble. That's why elderly people say young people mumble. And it's because of what you're learning here in acoustics. Humans can hear from 20 hertz to 20,000 hertz. But elderly people can't hear 20,000. They can't hear 18,000. They can't hear, let's look at it. Let's read our notes. Let's see what the elderly lose in terms of their hearing. Okay? Hearing, humans hear from as low as 20 hertz up to 20,000. And look at this. Put a star by this. Our very best hearing is for sounds between 1,000 to 4,000 cycles per second, or 1,000 to 4,000 hertz. Pull 1 to 4,000 hertz is where the letter S lives. It's where the letter F lives. It's where the letters CH live. It's where the letters SH live. It's where the letter T lives. Say T, and don't say T, it's T. Say CH. Say SH. Say K. Say F. Say S. So if you say those sounds, those are all frontal lip sounds and lip sounds. They don't come from the throat. Sounds that come from the throat are vowels. A, E, I, O, U. Music. Da, 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 da. Music is low pitched. Vowels are low pitched. Consonants are high pitched. Okay? And that's what the elderly lose. So when we talk about a hearing test, look what I said in italics here. Can you see the power? Do you see the Microsoft Word notes here? I want to make sure we're all looking at the same screen. Good. Thank you. Hearing tests are called audiograms. Circle that word. You're going to be taking a test, a course next semester called audiometry. Okay? Audiometry is the testing of human hearing. Hearing tests, audiograms, show human hearing sensitivity from, circle these two frequencies, 125 to 8,000. 125 up to 8,000. 125 to 8,000. I wonder if I have a picture of that. Not sure. I might. Yeah, look at this. Beauty. I'm glad I do. Ha ha ha. Can you see this picture here? Have a look. I'm going to blow it up and make it bigger. There it is. Now don't worry about the top yet. Don't leave all of this alone. Just don't look at that. Look at the square. This square is called an audiogram. On the left, you'll see 125. That's the lowest frequency at which we test human hearing. And people 125 hertz. Has anybody here taken music? Does anybody I never studied music as a kid. My parents never made me play piano or guitar or anything like that. But in music, okay, 125 hertz is called low C in music. Low C. If you double the frequency, and I'll show you here, if you double that, 125, you're now at 250. 250 hertz is middle C on a piano. If you double that, whoa, if you double that, you're at 500 hertz. That's high C on a piano. So you got low C, middle C, high C, okay? When you double 500, now you're at 1,000. You're out of the range of music. Okay, you're out. Music is all generally down where I'm circling. And if you double 1,000, you're at 2. And if you double 2, you're at 4. And if you double 4, you're at 8. When you double the frequency, it's called you've gone up 1 octave. An octave means a doubling of frequencies. So how many octave frequencies do you see in this audiogram? Let's count. 1, 2, 3, 4, 5, 6, 7. We test 7 octave frequencies. Every time you double the frequency, every time you double the hertz, you've gone up an octave. Music, low C, middle C, high C, but look at here, our best hearing, our human hearing, and now I'll draw your attention to the top. Look at this bump. That bump shows you the resonance of your outer ear canal. Here, I'll hold my cup here. Pretend it's Christmas and it's filled with wine. Okay, like a pop bottle. Your outer ear canal resonates between 1,000 and 4,000 hertz. In other words, your outer ear is made for speech. It's married. That's the way we were made. Okay? The shape of your outer ear and the length of your ear canal are designed literally to resonate with what? Sounds between 1 to 4,000 hertz. Why? Because that's where the consonants live. Look at here. Look what I'm circling. Told you. Okay, those are the consonants. And look at this. Look at the numbers going down the side. The numbers going down the side are what we're going to cover in a week or two. Those are called decibels. Okay, so frequency is on the horizontal, decibels is on the vertical. So look at the letter, look at these letters, all of them. Now put your hand to your throat. All of you, I need you to do this because otherwise you won't get it. Okay, say J, J. Say Z, Z, D, B, U, E, A, R, U, E. All those sounds make your throat vibrate. All of those sounds are, look where I'm circling, louder and low. L and L, loud and low. But look at the consonants. They're high-pitched and they're soft. So the consonants are soft. When you think of think of a name like Paul, a guy's name is Paul. Okay, what's the loudest part of the name Paul? All. If I yell, Paul, come here, Paul. The P isn't loud. If I say the word speech, what's the loudest part of the word speech? E. The isn't loud. Say church. What's the loudest part of church? Okay? The softest parts are the ch. That's what I mean. So the outer ear is literally made to amplify the high-pitched consonants. And consonants tell you what the word is. Dishes or fishes. Okay? Church, perch, lurch, search. Okay? It's very important. Vowels just take a word like a snowball and throw it. Vowels don't tell you what the word is. You've got 5 vowels in English. You have thousands of words. All those thousands of words have to share 5 vowels. So vowels are cheap. They don't tell you jack. It's all about the high-frequency consonants. They are what tell you what the word was. And elderly lose high-pitched hearing. So they can't hear what you said. And if you raise your voice, you're just making your vowels louder. But that's not what they have trouble hearing. They have trouble hearing the consonants. That's why hearing aids, what you will be fitting in hearing aids tend to amplify treble. Hearing aids don't amplify bass. Okay, you don't want to amplify bass. The elderly people have no problem hearing bass. Here's what the elderly hears. Look at the screen. I'll show you here. Look at the X's and O's. You see these X's and O's here? The X's represent the left ear. The O's represent the right ear. Okay? You can see that this person has good hearing in the lows. He can hear 125 hertz at 15 decibels, no problem. 1,000 hertz, though, it takes him about 40 to 50 to hear. And 2,000 and 4,000, it takes about 50 or 60 for the guy to hear. If you had normal hearing, you follow my cursor, all your X's and O's would be on the top, meaning it didn't take very many decibels for you to hear all the sounds. But when you get presbycusis, you have what they call a sloping hearing loss. You can't hear the highs, the treble. So look at this, you can't hear these consonants. That's what this all-important picture represents. Okay, good. We are now halfway through today's talk. Okay, we've covered period and frequency, and we've talked about the range of hearing of humans, and we've talked about the implications of hearing loss in humans, and what that means. And we even mentioned what we're going to look at later on today, a little bit about the outer ear canal. We'll be revisiting that this afternoon in anatomy class. Okay, because right now by you in the middle of the country, it's 12 noon, and in Maryland, you're at 1 p.m. already. I'm sitting here on the West Coast, it's 10 a.m., okay? Hours behind you. Anyway, enough on that. Let's go to talk about the next thing. And the next thing we need to discuss here is wavelength versus frequency, right here, wavelength, the bottom part of the page. So you've got period is 1 over F, F is 1 over P, that's your first set of formulas. Now you're getting to your second. And by the way, BTW, okay, by the way, it isn't all formulas. There's only 3 in this course that you need to know. We've already covered one of them. Now we're covering the second one. And what does the second one deal with? The second one deals with wavelength, not the period, not the time it takes to complete one cycle. Now we're going to talk about wavelength, the physical length of a sound wave. We'll take off your watch. You're not talking time anymore, so forget period. Now we're talking the physical length of a sound wave. How long is a cycle? How fat is it? How big is it? If we go all the way to this slide here, looky, how long is one rarefaction and one compression? One cycle, one rarefaction and compression. How physically long in feet or inches is it? Good. Now we're talking. Now we are cracking. All righty now. Wavelength versus frequency. Frequency, just like period, Wavelength is also inversely related to frequency, just like period was. So put a star by this one, okay? It'll help you, like a GPS system will guide you home. Let's look at your PowerPoint slide here and help to understand that too. Here we go. Here, okay? This one has a higher frequency than this wave. Okay, you all with me? Everybody look at the screen, make sure we got this. The top wave has a higher frequency than the bottom wave, so the top wave has a shorter period, but the top wave also has a shorter wavelength. Look at the bottom wave. It is a lower frequency, it has a longer period, and it also has a longer wavelength. So please remember with me, the higher the frequency, the shorter the period. The higher the frequency, the shorter the wavelength. The lower the frequency, the longer the time is, the longer the period. The lower the frequency, the longer is the physical wavelength. So both period and wavelength are inversely, they go opposite to the frequency. Good. So here we go. As it says here, as frequency increases, wavelength decreases. Recall, period is also inversely related to frequency. But wavelength now involves the speed of sound. This is where stuff gets trippy. This is where it gets really cool. Remember what we said last week about the speed of sound? Remember what we said last week about the speed of light? How fast is the speed of light? In the USA, you guys talk in miles. So light travels 186,000 miles per second. That's disgusting. Okay, what's the circumference of the Earth? 25,000 miles. Well, in 1 second, light travels 186,000 miles. See, in 1 second, light would circle the Earth a whole bunch of times. It's insane. Okay, nothing can go faster than the speed of light. Nothing. Okay, the sun, I said last week, how long does it take light from the sun to get to the Earth? 8 minutes. How long does it take light to get from the moon to the Earth? 3 seconds. You know how far away the moon is? 250,000 miles. Takes 3 seconds. Okay. So what's the nearest star? The very nearest star to us. The light took 4 years to get here. That's how big space is. That's how big outer space is. Okay? But sound is insanely slow. See, light doesn't need molecules to travel. Light can travel through a vacuum. Light can travel through outer space. Sound can't. Sound needs a medium. It needs metal, earth, air, water. Sound's got to go through something. Otherwise, sound can't travel. Okay? So let's look at what is the speed of sound in air. With good old air, the way we hear. The speed of sound is at the top, right here where I'm circling, right there, 343 meters per second, right here, right where I'm. Now, what's a meter? Make sure we Americans know what a meter is. It's about a yard. What's a yard? 36 inches? What's a meter? 39. So close enough, okay? And you don't even need to know the 3. Just say 340. 340 meters per second. Now, that's a little slower than 186,000 miles per second, okay? So sound is like a snail compared to light. That's why you see the lightning first and you hear the thunder later, okay? Light travels faster than sound. Good. Now, what's the speed of sound in terms of American feet? 1,130 feet per second. So either way you figure it, 340 meters per second, 1,130 feet per second, either way, doesn't matter. But let me tell you something. Science uses metric. Nobody uses feet. Okay? People just don't do it. We talk about it in terms of how fast does the jet go and how fast are you driving, 60 miles an hour, blah, blah, blah. But you should know, and it's probably good for you to know this because this is the outside world. 60 miles an hour is 100 kilometers an hour. I'd memorize that if I were you. Okay, 60 miles is 100 kilometers. 30 miles is 50 kilometers. Okay, it's important. This is just 50 miles an hour is 80 kilometers. It's good to know how the how the entire rest of the world functions. Americans are the only ones stuck on feet and inches and miles. Nobody else is, but nonetheless, the speed of sound in air is constant. So memorize what it is in terms of meters and memorize what it is in terms of feet. It's 340 meters per second or 343, take your pick, I don't care. And it's 1,130 feet per second. And by the way, let's just put 1,130 feet per second in terms of miles an hour, and it'll help you figure it out. Let's do that, just so that you get a good, healthy understanding of it. It's more fun to have it down. I'll scroll over to page 3, right here. At room temperature, speed of sound is about 340 meters per second, or 1,130 feet per second, or, look what it says at the rest of that sentence, about 1,238 kilometers an hour, or about 766 miles an hour. Circle that. Because how fast does a jet go? Have any of you flown in a jet before? You ever flown before? How fast does a jet go? About 550 miles an hour. About 600 miles an hour. About 500 to 600 miles an hour. That's the speed of a jet flying from Chicago to St. Louis. Flying from Baltimore, Maryland to wherever. Jacksonville, Florida. You get on the jet, it's going to go about 500 to 600 miles an hour. Well, how fast does sound travel? A little bit faster than a jet. A little bit. 766 miles an hour. It's good to know that. It's just, I don't know, information is good. That's why you go to school. You figure out new things. And what is the speed of sound called? It's called Mach 1. M-A-C-H 1. Mach 1. So when a jet breaks the sound barrier, like we're going to talk about next week, you can go faster than the speed of sound. Oh, yeah. You can't go faster than the speed of light. Nothing can, but you can go faster than the speed of sound. And when you go faster than the speed of sound, you break the sound barrier. And I'll tell you just a fun little thing. Have you ever snapped a towel at somebody in the locker room? Has he ever kind of done this thing and whoosh? Okay? Yeah. You know why it hurts? Because the tip of the towel has broken the sound barrier. Because just like when you crack a whip, whoosh, that is the tip of the whip breaking the sound barrier. Isn't that cool? No wonder a snap hurts. The snap of a towel hurts. It's like puts a welt on your leg. No kidding. Because the tip of that towel has broken the sound barrier. No wonder that little sucker hurts. Okay? Anyway, just now let's talk back to our second formula so we can complete this morning's talk. Let's look at your notes and let's talk about wavelength. Wavelength involves the speed of sound. Now, right here, okay, look where it says that. And now look at this right here. Wavelength equals speed of sound divided by the frequency. And the speed of sound, people, is always constant. You can call it 340 or you can call it 1,130 feet per second. Okay? But don't mix up miles and feet and meters. If you're going to work with meters, stick with meters. If you're going to work with feet, stick with feet, okay? But let's work it out together. Wavelength equals speed of sound over frequency. For example, 5 is equal to 10 divided by 2. So think of the 5 as being wavelength, 10 as being the speed of sound, divided by 2. Wavelength equals speed of sound divided by frequency. Look at the next one. Frequency equals speed of sound divided by wavelength. And look at the numerical ones I give you as an example. 2 is equal to 10 over 5. Okay? And look at the bottom one here. Speed of sound equals frequency times the wavelength. 10 is equal to 2 times 5. So these are all you're doing is manipulating little fractions here. Wavelength equals speed of sound over frequency. Frequency equals speed of sound over wavelength. Speed of sound equals frequency times wavelength. And the examples I'm giving you are right here. 5 is like 10 over 2. 2 is like 10 over 5. 10 is 2 times 5. Same thing. 6th grade arithmetic. That's all we're doing here. So here's your formula. Often in physics they call wavelength lambda. Don't worry about that. Leave that alone. I couldn't care less, so don't worry about this little weird Latin word here, or Greek, or whatever it is. I think it's Greek. Okay, don't worry about that. Wavelength equals the speed of sound, which is constant. Okay, in air, it's 340 meters per second, or 1,130 feet per second. That's a constant value, okay, divided by frequency. All right, speed of sound, wavelength equals speed of sound over frequency. And I actually could just kind of, boom, there you go. That's where I should put the HZ. See that? Wavelength equals speed of sound over frequency. Now let's do an example. Let's do it just like we did with period. For 100 hertz, wavelength, now look carefully at this. Don't freak. Every year people freak. And it's just like, wavelength over 1. That's what you always do. Wavelength equals speed of sound divided by the frequency. 340 meters per second divided by 100. Okay. Take your calculator. 340 meters per second divided by 100 hertz equals 3.4 meters. All I did was take 340 and divide it by 100. 3.4 meters. That's the wavelength of a 100 hertz tone. Let's do 1,000 hertz, just for fun. Or let's do it in feet. Let's do it in feet. Here you go. Talk about feet. Because now we've gone south of the 49th and we're in the good old USA. We're in Trump country now. Here we go. Okay? Wavelength over 1 is equal to 1,130 feet per second divided by 100. Okay, 1,130 divided by 100 equals 11.3 feet. Oh, don't ask me. It's what the calculator said. So look at, now imagine that. A 100 hertz tone, a 100 hertz tone is 11.3 feet long. That's long. I mean, that's a big wave. That's like, here, watch me. That's like from this doorway here all the way to the computer screen. That's pretty long. Okay, let's look at some other examples in your notes. Share screen. 250 hertz. 343 meters per second divided by 250 is 1.37 meters. Or 1,130 feet per second divided by 250, that's 4.5 feet. Can you see how the wavelength got shorter as the frequency went up? 250 is a higher frequency, so its wavelength got shorter. Let's do 8,000 hertz. 343 meters per second divided by 8,000 is 0.04 meters. Now, what the heck is that? 0.04 meters. Well, let's learn our decimals, okay? Let's make sure we do. If you've got two numbers behind the decimal, 0.04, that's 4/100ths. Now, if you have a meter, which is about 39 inches long, what's 0.04 meters? That's going to be 4 centimeters. Centimeters, a meter contains 100 centimeters. A centimeter is about like your fingernail. So if you're looking at a centimeter, 2.5 centimeters is about an inch. Okay? That's a good way to just... So you guys think in yards and inches, but let's just talk about metric. A meter is 39 inches long. What's 1/100th of a meter? A centimeter. What's 1/100th of a centimeter? It's my fingernail divided into 10 slices. Okay, a millimeter. So you have 100 centimeters to a meter. So what's the length of an 8,000 hertz tone? 343 divided by 8,000 is 0.04 meters. That's going to be 4 centimeters long, 4 fingernails long. So an 8,000 hertz tone is probably going to be about this long. Okay? It's about 2 inches long, about the width of my fingers. That's the length of an 8,000 hertz tone. So when you go higher and higher up in frequency, the wavelength gets shorter and shorter. When you get lower and lower and lower in frequency, the wavelengths get longer and longer and longer. And that's what I need you to grasp, because that has a lot to do with hearing aids. Okay? Read this. Important concept for people who fit hearing aids. Low frequencies bend, highs bounce. Low frequency waves are long. Look what it says here. They have long sound waves, and long sound waves bend around objects. And long sound waves are what elephants make. Think about the big ears on an elephant. And elephants are huge, and they emit sounds that are below 20 hertz. We can't hear them. And 20 hertz, what would be the wavelength of a 20 hertz tone? Let's calculate it. Turn it on here. 340 meters per second divided by 20 hertz equals, holy shit, 17 meters long. Yeah. 17 yards long. Okay, so that's a long, long sound waves. So long sound waves can bend over rocks, around trees. They can go over the hill and down into the next valley. And that's how trains of elephants know where each other is from miles apart. They are emitting low-frequency sounds that bend. And bending kind of sounds can go around things. And now think of the opposite. Think of bats. High-frequency, little furry mice flying through the air at night as it's dusk. The sun is setting. And you hear the bats. Can you hear them? I can't. But they're emitting extremely high-frequency sounds. And they've got these weird little ears, right? And the sounds they are emitting are high frequency. They don't travel any faster. All frequencies travel exactly the same speed. How fast? 340 meters per second, or 1,130 feet per second. So don't think frequencies travel different speeds, because that would be an acid trip, okay? All frequencies travel the same speed. But bats emit high frequencies, like 60,000 hertz. So those waves are tiny, 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 tiny. And little tiny waves don't bend around things. They're too short. They bounce off of things, okay? Lows bend, highs bounce. So bats use high frequencies like radar. They bounce off the bugs, and that's how the blind bat knows where the bugs are. It can catch the bugs at night, doesn't need light. It's using sound waves that bounce off of the bugs, and just like sonar on a submarine, you can detect where things are. Well, bats use high frequencies to detect where bugs are. Where did the sound bounce back? Oh, the bug must be here. Okay? So in hearing aids, have you ever heard someone's hearing aids whistle? Well, that's high frequency sounds that are bouncing off the guy's eardrum. And they are leaking out of the hearing aid, and they're getting picked up by the microphone of the hearing aid, and the hearing aid is amplifying the sound, spitting it out at the eardrum, and it's bouncing, it's leaking out, and okay, and lows won't do that. Lows bend. Okay, lows are too long, but highs bounce off. And those are the ones that are going to bounce off the eardrum, bounce off, and they're going to get picked up by the mic. Just like when you are talking in a mic and you go too close to the speaker, and now the speaker's sound is coming into the mic, not just your voice, but also the speaker's sound. Now you're getting what's called feedback. And the whistle in hearing aids is feedback. Sound leaking out of the hearing aid is getting picked up by the hearing aid. So you're getting a vicious circle. Just like talking into a mic when you're too close to the speaker, now not only your voice is going into the mic, but also the speaker's sound is going into the mic. And that's what causes the whistle. That's feedback. You get that sharp ee. Well, the whistle in people's hearing aids is feedback, and feedback occurs with high frequency sounds, not low. And because hearing aids are amplifying treble. It's all the elderly have trouble hearing treble. So hearing aids are treble emphasis. And they're going to be very prone to feedback. Yeah. So you can get a bit of a clinical grip of the field, but you're looking at it from what you've learned in the physics of acoustics. And it's very important. So today we've covered period and frequency, inversely related, wavelength and frequency, also inversely related. Period refers to the time it takes to complete one cycle. Wavelength is the physical length or size of the wave. Next week, we will finish this section on wavelength, speed of sound. Next week, we will talk about, well, we talked a little bit about the speed of sound, but we'll talk about density and elasticity, but I want you to read this ahead of time. Read the notes carefully, and if you have questions, ask me. And read what it says here about the Doppler effect and about the sonic boom. It's good for you. It's all good for all of us, okay? We'll talk about the Doppler effect next week. We'll talk about the speed of sound. The Doppler effect is kind of cool. You hear a cop car coming toward you or an ambulance coming toward you, and as soon as it passes you, that's the Doppler effect. Indianapolis. How come a car coming toward you, the pitch goes up, and as soon as the car goes past you, the pitch goes down? Okay, the Doppler effect. We'll talk about the speed of sound in terms of when a jet breaks the sound barrier. We'll look a bit more at that. And then we will complete things, moving on here, and talk a little bit about sound fields, rooms, classrooms with hard walls that have a lot of reflection versus rooms that are have carpet on the side. You've been in loud restaurants with the scraping of chairs, and you can hardly hear because of the din, the noise in the restaurant. There's lots of ways to control background noise, and it's by putting carpets on the walls so that sound gets absorbed and doesn't bounce off the walls. That's called reverberation. Reverberation, a lot of reflection and reverberations wreak havoc for people wearing hearing aids. We'll talk about the difference between an echo and reverberation. What's an echo versus reverberation? An echo, when you yell across Grand Canyon, hello, 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 versus a basketball bouncing in the gymnasium. Bow, 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 bow. All right? We will talk a little bit about anechoic rooms, soundproof rooms. We'll talk about sound-treated rooms, because this is how we test human hearing. And then we'll have a little bit of physics here talking about resonance. And that's how we're going to finish next week. We're going to be talking about resonance. We'll be talking about resonance in terms of impedance and resistance. We will be talking about opposition due to sound because of its mass. And let me just kind of give you an idea here where we're talking. Mass. What is that? Weight. It's like a locomotive of a train. Lots of mass. Duh. Okay? Versus stiffness. Something that's really, really stiff. Okay? All objects have mass and stiffness. Mass resonates with low frequency sounds. When you're in the house and the neighbors upstairs are playing music really loud, what comes through the ceiling? The bass guitar and the drums. Okay? Boom, boom, boom. Because the ceiling has mass, and mass resonates with lows. Stiffness doesn't. Okay, if I have my hand really, really stiff and I try to move it up and down slowly, I'll run into a lot of opposition. But if I jiggle it, no problem. Stiffness resonates with high frequencies. Okay, so when you want to make buildings earthquake proof, make them very stiff, because stiff objects do not resonate with slow movement. Okay, and that's what they do in Japan, because they're very prone to earthquakes. Anyway, all objects have mass and stiffness, and mass and stiffness together create what's called the resonant frequency of an object. The resonance of an object is its favorite vibrating frequency. The wine glass on Christmas Day. Your ear vibrating with high frequencies of sound. Why does it do that? Because of its particular mass and stiffness properties. Those things determine the resonance of an object. So that's how we finish this Unit 1. So that's what we'll do next week. Anyway, we covered the meat and potatoes today, and that was period inversely related to frequency, wavelength inversely related to frequency. Next week we'll talk Doppler effect, speed of sound, and we'll talk about sound fields like anechoic rooms, reverberations, echoes, and we'll finish off with mass, stiffness, and resonance. All righty then. We'll call it a day now. I'll talk in my best Scottish now. Oh, aye. I remember one time I used to work at the juvenile detention center in Calgary, and there was a worker there named Frank McLoone, and there was a kid named Curtis who missed the ball in basketball. He missed the hoop, and Frank goes, "Oh, hard luck, Curtis." "Oh, hard luck, Curtis." It was great. Okay, you guys. That's it for now. In about, I don't know, in about an hour or so, I'll meet you all for 120 anatomy. We'll do some anatomy then, and kind of we'll cover the outer ear and specifics, okay? Always remember these things are recorded, so someone can't make it, you can always listen to it later. Anyway, cheers. See you when we look at you.
Thank you.
You bet. Hey, hey.